All right, good afternoon, everyone. Let's get started. 12 o'clock. Welcome to Lecture 16, Computer Organization. So how you folks are doing? Good, good. I know some of you have something in Fox coming up, right? Is it tomorrow? Oh, yeah, so it's the midterm in Fox tomorrow. All right, good luck to all of you. Fox is paying, well, maybe a little bit, but it is really foundational to many other things. So just try to open your heart to Fox. Okay, so yeah, and it looks like a very dull, rainy day in Troy today. So I guess it's good that we all gathered here so we can have some fun with Comporg and floating point numbers, and hopefully we get to also talk about memory. Okay, yeah, 8 o'clock for Fox is kind of brutal. So I'm on this one with you. So I prefer to sleep at 8 o'clock rather than taking tests. But that's the schedule we have. Quite often we have not much of a choice. Okay, so arriving late for the lab, I think we give you like 5 or 10 minute leeway, so that should give you reasonable time to arrive to your lab, and we still count it as arriving on time, right? I don't think your exam should be more than 10 minutes over time, because if it is, then it's kind of it's a problem. Okay, so. All right. So hopefully all our panelists for today are in. I can see Charles responded something, so at least I can see. Yeah, I think it's a good idea to have those test questions so that we can basically check attendance of which of our panelists are in today. So other panelists, please answer something to that test question so that I know that you are here. And we need to get started. So let me start sharing something to keep you entertained. And first thing I wanted to go to was my Sublime. All right, and I need again to rearrange my windows because Webex software never remembers. And Q&A. Yeah, I'm glad you folks appreciate that there is no final exam in Homburg. There used to be, but not anymore, because you have 7 exams. It's brutal enough, so it wouldn't be fair to torture you with the final exam on top of that. When do we start working on the project? Within the next, I would say, couple of weeks, I should post it. Okay, and thank you for reminding. What was the Comporg final like? Well, it was like any other final. It was during their week of finals. It was 3 hours, and it was cumulative. So all the material. So that's a starking contrast with our exams that happen throughout the semester, because those exams are only on the topics that we covered. What is subject of the project? I haven't decided yet. I will tell you the truth. Maybe it will be some, most likely it's going to be a programming assignment, like writing 10,000 lines in MIPS, something along those lines. I'm just kidding. Not 10,000 lines, no. Yeah, most likely it's going to be a programming assignment. And most likely it's going to, well, most likely, all right, I don't want to say anything because I haven't decided yet. So once it's decided, I will let you know, okay? All right, so for today, Lab 5 is tomorrow. And so it is, kind of programming C. I know many of you love C, so it's another assignment in C, so you will need to write a logic simulation. And please make sure that you follow the idea. So if you look at their C file that we provide you as starter code, it kind of hopefully makes it clear what we expect. So do not use, like, if you have to build an ALU, do not just use C conditional statements if and plus, minus, multiplied, and so forth. Okay, so that's not the idea. That would not be a true simulator. That would be solving their problem using their methods, the features that C has. So the idea behind Lab 5 checkpoints is to actually build a very, very, very original, very close, very authentic simulator, so that you first write function to simulate each gate, and then you kind of build from those functions as building blocks. You build larger components like ALU. Okay, so make sure you review that code, because that lab is actually, it can be tricky to some of you. Okay, so take a look sooner rather than later. Definitely try to look before showing up in the lab, just to know what to expect. And of course, as usual, their TA and mentors in your lab will do a sort of a briefing to let you know what is expected and how to proceed. But the programming part itself is going to be easy, but figuring out what needs to be done, and especially setting up the unit tests and making sure that all your unit tests are meaningful and pass, that can be a little, that can take a little time. Okay, so someone already finished it. Okay, that's even better. Okay. All right. Today's slides are chapter 3 beyond submitted. That is correct. Yes. Okay. And so anything else I wanted to say? Okay. So lecture 16, poll 1 is actually already open. And this is part of the deal that we made in the very beginning of the semester, that I will, in the middle of the semester, and then another time at the very end of the semester, I will look at the submittee forum, I will look at the statistics, and I will collect the names of all students who were helping other students on the submittee forum. And then I will present those names to you in the form of a submittee poll, and then you will have a chance to vote for people whom you think were most helpful in answering other students' questions. Okay, so this poll is exactly this poll number 1 for today's lecture is exactly on this. So please vote for the people whom for the students. So I, of course, excluded all the TAs, mentors, and myself from this shortlist. So it's just other students, and that's why you don't see their full name. You only see the first name and their first letter of their last name. So that should be sufficient, hopefully, to identify specific people. And as you remember, part of the deal was that only people who decide to answer questions non-anonymously will be able to get this credit. Okay, so I just collected that list of I just compiled that list of people from submittee forum statistics. And if by any chance I left someone out, and their condition was like a person should have at least should have at least, I think, 3 or more meaningful answers to make it into this short list. Okay, so if I inadvertently left someone out, and you find that you answered 3 or more other students' questions and you're not in lecture 16 poll 1 shortlist, then please let me know. Okay, but I think I collected everyone again based on submittee statistics. And so then what's going to happen next? We, as usual, will keep this poll number 1 open for a few minutes, like half an hour, give or take, after the lecture. Then I will close the poll as usual, and then I will just look at the voting results, and the students who got their maximum number of votes will receive 1% towards their overall course grade. Okay, so that was part of the deal, and then, of course, we will do the same thing at the very end of the semester. That's going to be another 1 percentage point that we will be awarding to students who are actively helping other students on the Submit forum. And I've noticed that Submit forum is not particularly busy, so the traffic is pretty low. So it was, pretty hard to come up with even this list of this short list of nominations for people to receive this 1 percentage point towards the overall grade. So, we still have almost half of the semester in front of us and ahead of us, and so hopefully people can be more active. Okay, will be more active. All right. What's the progress on test grading? It is still in the process. The test is still in the process of being graded. We are moving slowly. I don't know if you've heard or not, but we lost one of the mentors who was helping us a lot, and we were not able so far to find a replacement. So, and we're still searching. So we're still trying to do something about it, and we had to kind of regroup our office hours a little. So we noticed that traditionally our Monday office hours are very slow. So probably noticed yesterday we decided to cancel one of our office hours yesterday. So that is also to make sure that we free TAs and mentors to do more of the grading or marking. Okay, because mentors they help us by doing marking. Okay, so that's that's what is happening. We are having some issues with of course the number of TAs and mentors that we have available for grading and marking. All right, so then, yeah, how is the exam grade overall looking? We haven't, we only graded, a few submissions from, a subset of the questions. It's too early to say. It's just not enough graded material to make any kind of conclusions. No, if you are taking this class, you cannot be a mentor, unfortunately. So the condition is a mentor is someone who took this class and did well. But if you know any of the friends who might be interested, then please send them, send them to Cheyenne because that might be an option. And yeah, it's tricky because we are more than halfway through the semester, but we are trying. Well, what is well in this class? Well in this class means A or A minus if in the worst case. So if you had a reason why you got an A minus, then you still probably be selected to mentor. If you had a B, I don't know. It's iffy. There's no really hard line. So it's all decided based on the applications that we get. So normally we get all the applications and then we select the people who we think are going to do best. And usually those are the people, who at the minimum got an A in this course. Okay. So then next question that I think interests many of you. So let's actually go through. So we used to do, to review the poll results, and then we kind of stopped. I was running out of time. So let's try to catch up with this, and let's look at, at least the poll results for the last couple of lectures, and then maybe we'll catch up with the rest on Friday. All right, so last lecture, Paul. Okay, so that was the voting on the hardest problem for test 4, and yeah, and 5 people thought that we're all the same level of difficulty, which I kind of actually tend to agree. But of course, you probably know where this question was heading. Okay, so I just was wondering if enough people would say that this test should have one of the problems nominated as an extra credit. And it looks like problem 1 is the one that we will make extra credit this time. Okay. So on test number 4, it's going to be again out of 80 points, and then problem 1, 20 points will be extra credit. All right. Well, if you spent so long on that one, it's, you only benefit from this. Okay. No, extra credit is not guaranteed to apply to all future exams. So it happened on test 3 and test 4. Okay, and yeah, that's that's the only 2 tests which, for which the decision has been made. Okay, so I heard from many students that they like this idea. So, but it's not yet guaranteed for the remaining tests 5, 6, and 7. Okay, and if I see some people are reacting with OOF and things like that. So if if people don't like this, this method of nominating one of their problems as extra credit after the fact, after the test, we can know, we can certainly stop doing that. Okay, so hardest is not equal longest, but it's very hard to kind of capture this idea in a single poll. Okay, so hardest may mean in some context the one that took you most of the time. Okay, it was hard to write quickly. Okay, if you will. And yeah, as someone noticed, I don't see how this nominating or making one of their problems extra credit can negatively affect anyone. It just means that the exam is out of 80 now. Exactly as I know. Thank you, Liam. Okay, I think it's exactly the right attitude. But if you think it affected you negatively, please let me know. If there is a concern that many students or some students share, we can just stop doing this. Okay, so the only reason I was doing this is because a few students told me that they liked it, and they wanted to continue that. But if it's no longer true, we can stop doing it. All right, so that was 15.1, 15.2. What was it? All right, to support subtraction, we need to make a separate subtractor instead of using the adder. Here I agree, it's false, right? We can, and we have seen an example how we just use our adder, and then instead of as a subtractor, right? So instead of doing a minus b, we just do a plus negative b. Okay, so we reuse the adder, and we just negate their second operand, and now we have our adder working as a subtractor. So I agree on this one. So then let's go quickly through 14, lecture 14, poll 1. All right, so here we were asking about their function. So you need an AND gate to compute it, and you only have you only have access to 2 input AND gates. So how many? So you will need to have several layers in your circuit. And the question was how many layers you need. And of course, it is log, right? So I don't know why so many people thought it would be exponential, right? It's exactly the opposite, right? So we have a lot fewer levels than we have inputs, right? Imagine you have 16 inputs. Are you saying that you're going to need 2 to the 16th gates to compute that the AND of 16 variables? So no, it's exactly the opposite way, right? We have the logarithm that crushes our, our 16 into 4. Okay, so and given 2 choices, if your log base 2 of n is not an integer, do you round up or do you round down? So are you taking a ceiling or are you taking a floor? And of course you're taking a ceiling, right? Because even if you have one extra input, you would have to and you no longer fit with the with a number of layers that would require that you would need if you didn't have that extra input. So with this extra input, you have to go with one additional layer. So you round it up, you do the ceiling. Okay, and no, we are not losing the grading rubric on the extra credit question. So actually, TAs did not know that we decided to make this question extra credit. So they grade the same. They grade all questions equally, or at least that is their intention. Well, the log answer appeared twice. No, it's not twice. One is, as you can see, this is their ceiling function applied to log2n. Here it is their floor function applied to it. Okay. Oh, you're saying the ceiling and floor didn't show up on the poll? Interesting. Okay. So then, sorry about that. I guess I will need to make then. Okay. So then I will take. Well, let's do this. Let me then just select that all answers would be correct. Okay. So I think. Were they different or not? All right. So let's check. And please do not answer this poll if you didn't answer before. But let me just quickly verify. So I will make it visible, and then I will. I'll look at this one. Okay, no, it's not. It's not the right. Okay, back. It's not this one. It's this one, right? Well, they are showing up in my view, right? So may not, you know. So especially if you highlight, you see that they're, those small, kind of things. Here they are on top. Here they are at the bottom. So that they are different, right? You can see that. All right. So then let's leave it like that. Yeah, sorry if you didn't notice, but you could always ask, right? That's what our Q&A is, and yeah, we only have 2 questions so far. Yeah, please serve more questions to Q&A so that people, our panelists who are handling them, have a chance to earn their water points. All right, yeah. Well, lecture polls, hopefully they're not worth that much. So even if something is not perfect, it's not really affecting you that much. So that was 14.1 and then 14.2. And let's actually see 14.2. Right, and the answer to this one was true. So I agree here with our majority student vote. So it does use the minimum number of gates in this particular case. It's not guaranteed though in the general case. So do not make any conclusions that would not be true. And then 14.3, which of these is the POS form of the truth table below? Okay, so the POS is product of sums. So we need to have a product. So that kind of immediately excludes these 2 options, right? Because they're not a product of something. They are a sum of products. Okay, and then out of these 2, you just had to look at their truth table and construct your POS form by looking at their corresponding rows in the truth table. And I believe this actually is not the right answer, but let me check myself. So it is 14.3. 14.3. And so there one I naught plus not I1. So that was their. Okay, no. So it is the, yeah. So for this one, I agree with the student vote. Okay, so it's this one. And I thought it was, worst come to worst, if you were if you were selecting between these two, it was pretty easy. You could just plug in some of the values, and you would definitely see that the incorrect option is incorrect. All right, so let's stop here for now, and then hopefully we can catch up with more lecture polls next time on Friday. But now we have to move on so that we cover the material that we need for you to finish your homework, which is due on Thursday. All right, as we decided to move it. And all right, so homework, and yeah, let's start with IEEE 754, this standard, and just general conversation about addition, subtraction, multiplication, and division. So, like, kind of continuing our conversation that we started when we were talking about ALUs, and then memory and that kind of stuff. We will try to cover today as well. But if not, it's okay. So our major concern is to cover these two topics: IEEE 754, addition, subtraction, multiplication, division. And of course, not just for integers, but also for floating point numbers. All right, and I'm going to the slides. So we can set aside the first 17 slides on memory, and then we will come back to them. And so we are starting. So it's chapter 3b, and we are starting with our conversation on arithmetic. And there is a number of common operations that we want to be able to perform on integers. And as we discussed earlier, this is really what allows computers to be called computers, right? They compute. So to compute means to perform some arithmetic operations like addition, subtraction, multiplication, and division. And there is a very important question that kind of is connected to any operation, any arithmetic operation that you might be performing, and that is the question of the overflow. And in your homework, one of the questions is actually asking you to think about the overflow and implement overflow correctly so that your SLT operation is now working as it should. Okay, because if you look at that question, I think it's question 8. It's a question from the textbook. There's only one in this homework, only one question from the textbook. So that one presents you with their diagrams for ALU, 1-bit ALU. And there are two diagrams because there is, as we discussed last time, there is difference between ALUs for all bits versus the ALU for the most significant bit, right? That's why they are slightly different, just because they're ALUs for different bits. And the context is, of course, we want to use them to create a larger ALU for 8 bits or 16 bits or 32 bits. Okay, so and then you need to reflect about the root causes of the problem that is described in the textbook, where if we compare -7 and 6, it turns out if we just look at the pure result that we see that it looks like -7 is actually not less than 6, and this is of course not true. And your job in that question is to fix that. Should we implement both kinds of 1-bit ALU? Well, it's up to you to decide. Do you need to make changes to all 1-bit ALUs used for both their most significant bit and all other bits, or do you need to maybe modify only one of them? So that is part of the challenge. This is part of the puzzle. Okay, and so then, of course, when we talk about integers, right, we spent a fair amount of time talking about integers, how they are represented, two's complement notation, and all that business. And things are relatively easy, as it turns out, with integers, because we can just perform operations very similarly to how we do our, our grade school addition subtraction algorithms, using just pen and paper with decimal numbers. And for floating point numbers, this is of course a lot more complicated, right? And then so we will discuss what it means, a floating point. So if there is a floating point, if there any other point? And it turns out that yes, we can also come up with an idea, and it's actually a lot easier to kind of comprehend of fixed point. So we can also have fixed point numbers, and we can have floating point numbers. And in many textbooks, in many resources, you might see this floating point real numbers. Well, like this, like it cannot be more wrong. We cannot have real numbers in our current digital systems. Never, not at all, not even in theory. Can someone tell me why? And when we say real numbers, what you should be thinking of is this, right? Do you remember this from math, or maybe some other courses? So this R stands for rational numbers. Stands for real numbers. Okay, so real numbers, yeah, would require that we have unlimited memory, because if you take any interval on your number line from A to B, you are going to have infinitely many real numbers. Obviously, in our current generation of computer systems, we cannot have infinite anything. Okay, we have limited memory, so we cannot possibly represent all real numbers even in a certain interval. And that means that the numbers that we're dealing with are not real numbers, right? Real numbers are in math, right? There is a concept of a real number, and there are also, but this is not what we can represent in computer systems, right? So when we talk about floating point, they actually correspond to the set of numbers that we denote by this, not this fancy R, but this fancy Q. Does anyone remember what this fancy math Q stands for? Rational, exactly. So they are rational numbers. So what is a rational number? Does anyone remember the definition? Yeah, Fox, you see? You're using their knowledge from Fox. Yeah, it's any number that can be represented as A divided by B. Okay, it's like a ratio of two integers, exactly. So by definition, any number that can be represented as a ratio is called, not surprisingly, a rational number. And the number of, so with current generation computer systems, we only represent rational numbers, right? We cannot represent, all real numbers, and not even, as it turns out, not even all rational decimal numbers we are able to represent exactly. So when we say rational, this rational means binary rational, not necessarily decimal rational. And there is a difference. So for example, if you think about 1 divided by 3, okay, it's, according to our definition, it's a rational number, but we cannot represent it as as a floating point with the same precision, right? We can only represent it approximately as 333, and then we would have to stop somewhere, right? We cannot represent the infinite number of threes. All right. So when we say Q, this Q, this rational, means that it's it's actually a binary rational number, and there is a difference, as we shall see shortly. For example, here's this very nice rational number, 1 divided by 10, which we can represent as 0.1. It's nice and beautiful, but it turns out that this nice and beautiful number, decimal number, right? So this is all decimal. we cannot represent with a finite number of bits. We cannot represent it exactly in the binary form, right? If we, if we keep the idea of a, floating, of a fractional number, right? So no matter how we try, we're gonna end up something, with something like, 9999, and then maybe 8 in the end, something like that. Okay, and of course it is close to 0.1, but it's an approximation, right? Because as it turns out, this 1/10 is not representable by a finite sequence of powers of 2. Okay, so if we have, so we can take, like 1, right? So 1 eighth and 1/16th, and so forth, right? So just sum of 1 over 2 to the power of I, right? Where this can be 1 or 0, right? So we either take some power of 2 or we don't take it, right? And I is from 1 to some n, right? So and we will see that, yeah, no matter how long our series is, we cannot we cannot make it to sum up exactly to 1/10. It's going to be either smaller or larger. Okay, and just for reference, and to make things easier, right, we can just do 1/2 is 0.5, 1/4 is 0.25, and 1/8 is 1.125. Okay, and then 1/16th is 0, 0, and 0.625. Okay, and we can actually see that if I took 1/8, then yeah, it's already more than 1/10. So no, 1/8 should not be in the sum to begin with, right? So we should take it as 0 divided by, or just cross it out. So it's going to be 1/16th plus, and then we have to see, do we take 1/32 or not, or do we take it as 1 or maybe 0? Okay, and so we are trying to find all those fractions, where at the bottom we have a power of 2, so that it sums up exactly to 1/10. And it turns out that we can't. All right. And so we are going to talk about floating point numbers, right? And how they're represented and how to perform operations on them. So let's start slow with things that are hopefully pretty straightforward, but they will stop being straightforward, pretty soon. For now, it's integer addition. So how do we perform integer addition? It's the same idea. It's the same thing that we would do with our grade school algorithm, just in binary. So if we have, and then in Zybooks we have a very nice animation that I wanted to use as I'm going through this material. So it's it's week number 8, and addition and subtraction, right? And so this is the same example that we have in the slides, just with the animation so that you can see the dynamics of it. So we are adding 7 and 6, so those are binary representations of them, and so then we just do it, bit by bit. We add 1 and 0, the result is 1, and the carry is 0. Okay, and so then we do the second bit. So we are adding 3 values, 0, 1, and 1. The result is 0, and there is 1 as the carry into the next bit. And then we do the third bit, 1, 1, 1. So the result is 1. Carry out from third bit into the fourth is going to be 1. And then 1 0 0, and then of course obviously the remaining bits are all zeros because we're just summing zeros. Okay, so exactly the same algorithm that we would use for adding decimal numbers we can apply to binary numbers. Just have to remember that 1 and 1 is not 2, right? We don't have 2 in binary system, so 1 and 1 is 0, and 1 is the carry into the next more significant bit. And of course, you can apply the same algorithm for hexadecimal values, right? You just need to remember that if you sum two hexadecimal digits in a certain position and the result is more than 15, it means that there is a carry into the next position, right? Because the base of the system is 16, so there is no such a digit as 16 or 17 or anything greater, right? So the only digits, the only numbers in the hexadecimal system are from 0 to 15, because 16 means we have 16 different digits or different values. All right, and so we can do the subtraction in a very similar fashion. So let's look at 7 minus 6. Okay, so we subtract 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 0 is 0, and so we have, the result is 1. Okay, so, or we can subtract by determining their complement. And let me pause it, and let me go back here. Let me pause it. All right. So by determining their negation of the number that we are subtracting, and we can do that. So basically, instead of doing 7 minus 6, we can do 7 plus negative 6. So to get negative 6, we invert all bits from 6 and we add 1 to the least significant bit, this bit. Okay, and that's what we get. Okay, so this is negative 6, and then we are adding them together, and here the algorithm is the same, right? So we added 1 and we got negative 6, and now we're going to be adding them normally, right? So essentially performing subtraction, but technically we are doing addition. So 1 plus 0 is 1, and we just do the same for all the other bits, and we end up with 1. Okay, so the result is the same. That kind of demonstrates that we were doing the right thing. All right, so, and yeah, if you're using Zybooks, there are a few practice exercises that you can work on, and there's even a challenge activity. Okay, so one observation that we can make is we can have a condition that would be qualified as an overflow, and this is exactly the problem that you have to deal in that homework problem that comes from the textbook, right? It's B.24, problem B.24, and we're gonna talk about it next. Okay, and yeah, your question about D flip-flop, please ask it in the Q&A. Q&A is very slow today, just 4 questions, and some of them were test questions. So we need to have more questions so that people can earn their points. Yeah, please. And memory, flip-flop is memory, so we're going to talk about it after we're done with arithmetic and floating point. Okay. You need, if you think you are co-host, yeah, I think this came up with with you multiple times. You're not actually a co-host today. So I added you once when you said you were, but I checked my records and you were not a co-host. So a co-host is someone who received an email from Cheyenne a couple days ago saying that they are a co-host for today's lecture specifically. Right? We have more people who signed up on the sign up system to be a co-host than we have slots. So Cheyenne manually selects a subset of people who signed up to actually be panelists today. Okay. Yeah, mail at sign up. It doesn't matter. It just means that you signed up. It doesn't mean that you are a panelist. So you need to receive an email from Cheyenne for a specific lecture saying that you are a panelist today. Okay. Yes. Sorry for the confusion, but that's what we had to do so that we could open the sign up for more people and then select a subset of them to give the opportunity to more people to participate. Because when we opened just 4 slots on sign up, they were filled up by the same set of people, and and it filled up quickly, and it was not fair to other students who also wanted to participate. All right, and now here is their overflow. So the overflow is their condition that signals us that the result is out of range. Okay, so for example, here we are adding 7 and 6, and their carry out from their most significant bit is 0. So the result is 13. It is, we are able to represent it with the number of bits that we are given, right? So it's 1, 2, 3, 4, 5, 6 bits in this case. So clearly 13 can be represented with 6 bits, and there is no overflow. Okay, so and then if we think about what an overflow is, we can draw certain conclusions. So first, if we are adding positive, right, that's a weird notation that they use on the slides for positive. So when we are adding positive and negative operands, we can never have an overflow, because if we had a positive value that was large enough to be represented given however many bits we had available, then this number is not going to be larger, right? It's only going to be smaller. And inversely, if we had a large negative number and it was somehow represented, then by adding a positive number, we are making this negative number smaller by the absolute value. So there will be no overflow guaranteed. And if we are adding 2 positive operands, then of course we can get an overflow. So here's an example. We have 1, 1, and 1, and we have so this is all right. This is 7, and we have 1, 1, and 1. Okay, so we have 4. This is also 7, and we are adding. And here we assume the 2's complementation. So this bit is is a sign bit. So its weight is going to be negative 2 to the 3rd. Okay. And so we are adding. So 1 and 1 is 0, and 1 is the carry. So, and now we have 1, and 1 is the carry, and we have 1, and 1 is the carry, and we have 1. Okay. So it turns out that, if we treat everything as 2's complement, which was our initial convention, then this would be that this 1 here would indicate that we have a negative number. Okay, because this first bit is has this negative weight, negative 2 to the 3rd, right? And obviously this cannot be possibly true, right? We need to have a positive result if we are adding 2 positive numbers. So why is it called overflow? Well, it's called an overflow just because, well, this is not really a sign bit, right? What we got here. But this was supposed to be a regular bit, right? The bit that has a positive weight. And we just ran out of bits. We just don't have enough bits to represent this value. So the true value should have been 14. Okay, and instead of a 14, here we got negative 8 plus 4 plus 2. So it's negative 2. Okay, and so that means that something is wrong. And what is wrong, we can see exactly if we try to look at all values with 4 bits using 2's complementation. So starting from 0, 0, 0 here, and 0, 0, 1, and so forth. And if we go up to This is going to be 7. All right, this is decimal 0, this is decimal 1. And then towards negative numbers, all right, we have this, and then this is negative 2, and so forth. And the largest by absolute value negative number would be negative 8. So that tells us that, well, we have no way to represent plus 14 using 4 bits in 2's complement notation. It's just not enough bits. We need an extra bit for that. Okay, and the overflow is exactly telling us this. We are adding 2 numbers that are positive, so their sign bits are zeros, and we end up with the result that in its sign bit has a 1. And this is an overflow. Okay, so when we are adding 2 positive operands, the overflow is when the result sign is 1, whereas both operands that we were summing were positive. And of course, exactly the same happens when we have 2 negative operands. So the expected result should be negative, so we expecting to see 1 here. So that would indicate a normal result, but in fact, the overflow result is 0. Okay, and so that means that we have such a negative number that it is less than negative 8 in this case. All right, if we assume just 4 bits, and it is not representable using 4 bits. We need more bits to represent that value. All right, so that's the basics of overflow, the idea of overflow. And so here is an example with a negation of the second operand. And this example, we looked at the animation in Zybook, so we have already done this. And again, overflow is when we are adding, when we are subtracting positive value from a negative value, and the overflow the overflow is when the result sign, the sign of the result, this most significant bit of the result is 0, or conversely, if we are subtracting a negative value from the positive value and the sign of the result is 1, it also means an overflow. So, if you look at the cases that we kind of looked at, so adding positive and negative operands never overflow. Subtracting 2 positive or negative operands never overflow. And the rest we can just number. This is case number 1, this is case number 2, this is case number 3, and this is case number 4. And we can then just capture all those cases in a table so that we have 2 cases for addition, 2 cases for subtraction, and then for each of addition and subtraction, we have to look at operands are positive, operands are negative, and then this is the condition that we will determine whether we have an overflow or not, right? Where x is the result, so if both operands are positive, but the result is negative, which means the sign of the result is 1, we have an overflow. And similarly, if both operands are negative, we kind of expect that the result should be negative in our traditional arithmetic. And if it's not, if we see that the result is actually not negative, it means we have an overflow. And for subtraction, we just, it's kind of very similar rules, but we need to make sure that the signs of the operands are different. So either when A is non-negative, B is negative, the result should be positive, but if we get a negative result, it means we have an overflow. And obviously, the last case is exactly the opposite of our third line, right? If A is negative, but B is non-negative, and we expect the result to be negative, so if we get a result that is non-negative, it means that we have an overflow. So what do we do with an overflow? Well, it depends. It depends on your hardware. It depends on your software, in particular your programming languages. Some programming languages, in fact, many programming languages. So C is just one example. Another example is Java. So many common programming languages, they just ignore overflow, and they kind of assume their attitude that, oh, it's the responsibility of the programmer to make sure that there is no overflow. So they do not help you in any way to detect overflow. And it can be painful. It's not a trivial thing to ensure that any operation that you're performing, like when you're writing C equals A plus B in C or Java, right? It's not trivial to ensure that A plus B, the result is not an not an overflow. Of course, you can implement exactly this overflow detection that we just described. But can you imagine doing this for any addition or subtraction that you perform? Like after doing, C equals A plus B, you have to have, what, call a function to determine whether, A, B, and C are such that it is indicative of an overflow? Or do you write like if sine of A is less than 0 and sine of B is less, or if A is less than 0, B is less of 0, and the sine of C is this, it's an overflow, right? You would spend more instructions doing this overflow detection after every single addition subtraction operation than their addition subtraction operation itself. It's very inconvenient, and that's why it's almost never done. Okay, so you just have to think about other ways to guarantee that your addition subtraction operations never overflow, and it takes some effort. It takes some thinking how to actually guarantee it for your code. If you just ignore it, you are not guaranteed from an overflow. So you might get an overflow, and many very known bugs in software are caused exactly by this. Imagine there's a counter, all right, that can be positive and negative, and you increment the counter, and suddenly from being positive, it turns out to be negative, and it wraps around, and your, I don't know, your Mars rover just, just gets disconnected, or your rocket just, destructs itself, or something like that, and you're responsible for multi-billion losses, right? Because you thought, you hoped you would never have an overflow, but in fact, it would be, you have an overflow and your code no longer functions correctly. Yeah, Y2K. Yeah, I remember that. It was a big, it was a big thing. It wasn't exactly the arithmetic overflow, but it was a problem that in many systems, the year was just represented with 2 digits because no one ever thought that they would, that the 21st century is just around the corner, and yeah, and so that was, of course, a problem. And if there was any math done with, with those 2 digits, decimal digits that correspond to a year, like you would end up in, instead of year 2000, you would end up in, year 1900 if the software was assuming the 20th century. Okay, so that was that was slightly different from the overflow that we are describing here, but it was also, yeah, it was a big problem. All right, so some languages, many languages just ignore overflow, and when their source code is compiled, is translated from those high-level languages into machine codes, into assembly language, they use the corresponding unsigned instructions. So for MIPS, we have add U for unsigned, remember, and you can even have add UI, right, where I stands for, of course, immediate, and correspondingly we have sub U. So that U means that the processor will ignore overflow, and it will just treat the numbers as always unsigned. And with unsigned numbers, there is no overflow, so it will just ignore it. So other languages like Fortran and Ada and a few others, they actually require raising an exception. So those languages would use, the compilers for those languages would generate instructions, assembly instructions that would refer to signed versions of the operations. So add without U means we are adding signed values, so we treat operands as 2's complement, as being in 2's complementation, add I without a U, sub without a U. So all those instructions correspond to signed versions of the operations. And so when overflow happens in those languages, they actually invoke an exception. So they generate an exception, which in turn invokes an exception handler. And then in case of MIPS, their current value of the program counter is saved in their special register EPC, exception program counter, and then their control is transferred to a so-called exception handler, and the address of the handler is determined, and we will talk a little bit more about how exceptions are handled in MIPS. So there are actually different ways of organizing exception handling. But either way, there is an address which corresponds to their handler, to their procedure that handles their exceptions, either all exceptions or there are multiple addresses. Each corresponds to a particular type of an exception. And then, of course, we can, this handler is just a code that executes, and it should have whatever handling we want to happen when this exceptional situation is encountered, okay, like an overflow. And there is usually there is no general solution, but we just need to make sure that we are able to detect this overflow, and then we can decide what to do with it. All right, so there is an instruction called MFC 0, move from coprocessor 0. So this C0 and MF instructions, we will see more today. So this moves, so our MIPS processor has several coprocessors, and they are numbered, coprocessor 0, coprocessor 1. So coprocessor 0 has their ability to retrieve that EPC value. So if we want to move it to one of our regular registers that we've, general purpose registers, then we can use this instruction, move from coprocessor 0, and then we know, so this EPC is like the return address, right? So after our exception handler is done execution, this EPC contains their program counter value to which we need to return. So we can continue execution of our program. Of course, and we will talk more about it. So in many applications, in particular graphics, media processing, it is more convenient to operate not on just one pair of operands, but on sets of operands or vectors that contain multiple bits of data. And so that calls for special design of hardware. And again, we will talk more about it. So for example, we can use a 64-bit adder with a partitioned carry chain, and that means that it just have multiple carry signals. And this adder would operate on vectors. So instead of adding just two 1-bit numbers, it would be capable of adding two 8-bit numbers, or multiplying two 8-bit numbers, and this can be partitioned differently. So instead of doing 8 by 8 bit, it can do 4 by 16 or 2 by 32 bit vectors, right? So in this case it's for the adder, but the same can be implemented for multiplication. So this 8 by 8 bit means it's 8 8-bit vectors. So 8 times 8 is 64. Or we can treat it as 4 vectors, but each vector is 16 bits, or 2 vectors and each vector is 32 bits, right? So this 2, 8, and 4 corresponds to the number of vectors, and this 8, 16, and 32 corresponds to the size of each vector. 8, 16, or 32 elements in a vector. So, and we'll talk more about SIMD, single instruction that operates on multiple data values, and that is one of the ways to increase performance. Remember, this course is a lot about performance, so we'll talk about SIMD later. And one other thing that can happen when performing operations is saturation. So, instead of just letting their value to wrap up and go to their most negative value from being close to the most positive, as we see what happens if we just use our two's complementation, we can propose a slightly different approach. When on overflow, the result is kind of capped at the largest possible value. So like if we are adding 7 and 7, then the result would be 7, right? Instead of -2, because 7 in using 4 bits and 2's complementation is the largest value that can be represented using that many bits. So, and so that's why it says compare with 2's complement modular arithmetic, right? So, and arguably that is a more this approach, this saturation is a better approach, because in our example that we saw before, when we add 7 and 7, we get -2, right? Here, what we are talking about is 7 and 7 is 7, right? Because 7 is the maximum value that we can represent using 4 bits into its complementation. So this is their saturation method, right? Which arguably is better because, well, the value that you get is not the real result, but it's closer. It's as close to the real result as we can get. Okay, and so that is desirable in many applications, including audio, video, right? So if you get the highest volume, at least you stay at the highest volume, right? You're not going down to the lowest volume, or something like that. So then multiplication is something that we can do with our grade school multiplication algorithm. So we have a multiplicand and we have a multiplier, and then we just look at the multiplier one bit at a time and multiply it this bit by the multiplicand, which means, because the only two values that we can have is 0 and 1, it means that we either copy the multiplicand as is, right here, because this bit is 1, or we just take it as 0, right? 0 times 1 triple zero, triple zeros is 4 zeros, and that's why we have it here as 4 zeros. All right, and for this, let's actually look at their Zybooks, because they again have a very nice animated version of this slide. So I will go to multiplication. All right, so here's an example of multiplication. So let's start, and you see how it works. So those are the values that we are multiplying: 1 triple zero and 1001. Okay, so digits are multiplied one at a time from right to left. So we take this digit of the multiplier and multiply it by the multiplicand, and take this partial product, and then we go on to the next digit, and each time we are getting a partial product. And so we have as many partial products as we have digits in the multiplier, 4, and then we sum all the partial products to determine the final product. Okay, and yeah, so that's our product. And it's an interesting observation that the product can have, and in many cases will have, more bits than our multiplicand or multiplier by themselves, and the max number of bits that we might need for the result, for the product, is actually twice the number of bits in the multiplicand and multiplier. So if our multiplicand and multiplier are 4 bits each, we're going to need 8 bits in the product. And so then I'm going to skip this. And then the hardware to implement this, it's also on our slide, just implements this exact method. And let's again play the animation, because I think it makes things a lot clearer. Well, before we do that, let's so this is our multiplicand, and we expanded to 64 bits, but it's originally a 32-bit value. So here you see this is our 32-bit value, and the most significant 32 bits are just filled with their, with a sign bit, which in this case is 0, right? So we just extend 32-bit value into 64-bit because we are using a 64-bit ALU. So because of that, a 64-bit ALU needs 64-bit operands. And then we will be shifting a multiplicand to the left because we need to, and this is exactly what happens here. See how the partial product is shifted left on every step of this multiplication. So we will be doing exactly this. All right, and so then 64-bit ALU, 64-bit product, and then our multiplier will be here in a 32-bit register, and we will need 1 digit of a multiplier at a time at each step, and that's why we're shifting right so that the least significant bit of the multiplier is taken here from this input, and then it is used to control this control test is the circuitry that generates all the control signals for the rest of the circuit. So, and let's do this one step at a time. So multiplier. All right, we start with a 0 product. We start with our full multiplicand. We start with our full multiplier. And the rightmost bit is 0. It gets here. Okay, and because multiplier, this bit is 0, multiplicand register is shifted left 1 bit, as we saw, and the multiplier is shifted right by 1 bit. Okay, as we also saw. And then next bit is 1, and so we take this 11010, sum it with a partial result, and write the new result to the product. So this is, this product automatically collects or sums partial results as we go. Okay, and so then shift left again, shift right again. All right, multiplicand is shifted left, multiplier is shifted right, and then we have this one. Okay, and their partial product summed with their product by this ALU. The result is written to the product and so forth. Okay, so that's exactly the implementation of, just straightforward implementation of our grade school multiplication algorithm, and that's the hardware that does it. Can we do better? Right. So this approach definitely works. Right. So let's first go through this. And on the left here, you can see a flow chart that describes the process of multiplication. Right. So we always test just the least significant bit of the multiplier, which in hardware is shifted here. Right. So this is the place where this bit appears. And if it is 0, we basically don't need to do anything. We just shift our multiplicand to the left because the partial sum is going to be 0. If this bit is 1, right, we have to take their multiplicand and make it into their partial product. And then this partial product, which will be here, is summed with their running total of product here. And the result is going to overwrite our product here. Okay, so this product is a running total, right? Instead of just having 4 partial products and then summing them up separately, we are performing the summation every time we get a new partial product. So we accumulate the partial product in this product register, which is of course 64-bit. Okay, so and we just do that for all of our bits, and once we if we have more bits to process, we just continue the loop, and when we are done, when we have done 32 executions, we are done, and then the product, so the result is here. This is our product, and the product the result of our multiplication. So here is the same example, just shown each step at a time. So we start with the product, which is 0. Okay. And then this is our multiplicand, and this is our multiplier. So we take the the least significant bit of the multiplier. It's 1, and that means that we just take the multiplicand 1, 0, add it with the current product. So we take this and this, we sum them. Okay, and that's why the result is 0, 0, 1, 0. Okay, exactly as this formula suggests. And then we shift left the multiplicand so that the next partial sum is shifted left, as we saw in our pen and paper grade algorithm. So we shift, all right, we take multiplicand, we shift it left by 1, and we get this, right? So the value that ends in 1, 0, 0. And then we shift right the multiplier, so this bit is shifted out, right? Because we shift to the right, so this bit is lost, but we don't need it anymore. It has already been processed. So now we have this is the least significant bit, and it's 1. That's why we take the multiplicand of this, right? Well, this whole thing, of course. And then, all right, so we are here, right? This is what we are summing, and this is what we are summing with. And so we take this sum, and this is the result, right? Ends in 1, 1, 0 because it's 1, 0, 0 and 0, 1, 0. So it's 1, 1, 0. Okay, and then we just keep going like that. So this is, like I said, just a step-by-step implementation of this, of this flow chart with this example. So can we do better? It turns out that yes, we can actually do better. We can build an optimized multiplier where we no longer need to have a 64-bit ALU, and where we, instead of shifting the multiplicand, right, we are shifting the product. Right, so the product register is 64-bit as it should be, right? There's no way around it. But we can use a 32-bit ALU. If we treat this product register, if we have this, if we treat it as kind of two parts. So this is the part where we store our partial results, and then we just keep shifting to the right, right? So we're shifting right this partial result. Okay, so we put something in here, and then we shifted the whole thing to the right. We put some next, product, and we shift it to the right. So this allows us to not shift the multiplicand, and this allows us to use the 32-bit ALU. All right, so it's 1 cycle per partial product addition. Okay, it's okay if the frequency of multiplications is low, so we can still do better, as we shall see shortly. But even this optimized is an improvement over the previous design that we had. Right, it uses it's a simpler method, and it uses the components that have fewer bits. So and note how we didn't even have to shift the multiplier. Right, so this method allows us to get rid of shifting the multiplier 1 bit to the right, as was the case in the previous scenario. And so this is exactly the method that we talked about. And so if we need to perform many multiplications, then even this algorithm is not the fastest. It's a little parallel because we do add and shift in parallel instead of completely sequentially in the previous design, but we can even do better. Of course, there's a price we have to pay if we want to have a faster multiplier, which is completely parallel. We have to throw in more hardware. Unfortunately, in this case, it is unavoidable. And what we do is we just compute each bit of the result of the product with its own adder. So those are adders, 32-bit adders. So see how we add the bit zero, how uh, we take the first partial sum and the second partial sum, and we add them together, and that determines the first 2-bit of the product. Okay, so they are immediately available. What about their second bit? Well, the bit that we would call product 2, well, we cannot determine it here, right? Because this would be product 2. It comes from product 1 and this partial sum, which we still need to compute. And we have a dedicated adder that computes this partial product from multiplier bit number 2 times multiplicand and multiplier bit number 3 times multiplicand. Okay, and so we end up with this faster multiplier that, as you can see, has multiple levels or multiple layers of adders connected like that. And of course, all adders work in parallel, and therefore we can get a significant performance increase. However, it comes with a cost because you see we had to use a lot more hardware. So it's the question, of course, of cost over performance trade-off. All right, so how many, the result, of course, is 64 bits. So the most significant bit of the product is product 63. And the question is, well, how many adders do we need to throw in here? So how many adders do we have at this level here, right, at this level? If we are adding 32-bit values, if we are multiplying 32-bit values. 16, exactly, right? Because each of them takes 2 bits, 0, 1, 2, 3. So we need 16. At the next level, how many adders do we need? 8, exactly. And then 4, and then 2, and then 1. Okay, and so if you sum up all of those, so it's 28, 31. Okay, so it's exactly 31 adders. It's a lot. It's a lot of extra hardware, but it's a price we might want to pay for the speed, right? Because in this case, imagine that each adder takes t time to perform the addition. How long will it take for the product of our multiplication to be computed? Yeah, 31 adders. That's a lot. So how many time would it take to compute our product in this scenario? It's 5t, exactly. So, and someone gave the formula how to compute the number of levels or layers, right? It's your favorite logarithm, right? So there are 5 layers, and therefore their latency, right? The amount of time to compute is 5t. Okay, and if you think about it, it's a lot better than what we had here, right? Because here, we have to shift by 32. Okay, so if this is t, then it would be 32t. Here it's 5t. Okay, it's a lot better. Okay, so now back to our favorite MIPS. So how do we multiply using MIPS? There are special instructions, and I know some of you have been using them in on the exams and elsewhere, even in cases where you didn't have to, because if you need to multiply divide by 2, it's a lot easier to use shift instructions. Okay, but if it's not by 2, if it's not multiply divide by 2, and you need multiplication division, you have to use dedicated instructions. So here are the instructions that exist in MIPS for multiplication. So mult and then we multiply these two registers one by another. And a note, there is no register specified to put the result in, because the result is saved in special registers called high-low, because the result can be 64 bits. Okay, so, and mult-u is the unsigned version of a multiplication instruction. So how do we then get the result out of those high-low registers? Well, it turns out there is a separate instruction, mf, a move from high or low, mf high, mf low, and then the argument is the register. So move mf hi, move from high register into this register, right? So it's going to be from high into this register, or from low into this register. That's how you can move stuff from those registers into, that contain the result of the multiplication, into your general purpose 32-bit registers. And we can also test the high value to see if the product overflows 32 bits. And in case we are absolutely sure that the result fits in 32 bits, or for some reason we want to ignore any result that does not fit into 32 bits, there is an instruction called mul, multiply, which multiplies rd by, which multiplies rs by rt, and puts the result in RD, but it only is going to produce the least significant 32 bits of the product. Okay, so if there are more bits in the result, there's no way you can get it. If you need them, in most cases you do, you need to use mult or mult-u with mf high, mf low. Okay, so you will not be able to do it with one instruction, because you will need to at least move the result using two instructions. First from high into some register, then from low into some register. The division, okay, it's the the elder sister of multiplication. So things are getting even more interesting with division. So, well, first we need to be aware of the zero divisor, okay, the division by zero. And then other than that, we can basically take the same approach that we did with multiplication. We just use our grade school algorithm, pen and paper, shown here. So then just perform this algorithm, okay? And then the corresponding hardware in the flowchart will be conceptually very similar to multiplication, except for with a division, we have to shift the divisor to the right. And remember, in case of multiplication, we were shifting the multiplicand to the left, so it's kind of opposite. And the quotient, we have to shift left. Other than that, it's a very similar hardware for division as we had for multiplication, and the flow chart is also very similar. So one thing is we actually need to have 33 repetitions here, not 32. And here's an example of division. Okay, so it just shows step by step how this division hardware works. That is on this slide, and again, it's very similar to multiplication, just kind of in the opposite direction, if you will. So I'm not going to spend too much time on it. And if you're using Zybooks, then you have this animation available to you. But if you're using a regular textbook, you could just follow this slide to see how their quotient and the remainder are formed, one by one, right, step by step, and different from the multiplication. Of course, the result of the division is the quotient and the remainder, right? We need to know both. Both are parts of the result of the division. We cannot ignore, sometimes we can ignore one, one or the other, but in the general case, we need to know both. And this is the optimized divider. Again, we want to have less shifting, and we want to use a 32-bit ALU instead of a 64-bit. So same idea as previously with the optimized multiplier. And the faster division, lucky for you, there is no easy parallel hardware similar to the one that we saw for the multiplier, right? We cannot just throw more adders and get the division done faster. There are ways of doing faster division. So one of them is known as SRT division, right? SRT just stands for the names of the inventors of this method that allow us to generate multiple quotient bits per step. But it's still this algorithm, even their SRT, and there are other algorithms for division, they still require multiple steps. So things are more complicated than with their multiplication, so we're not going to even talk about them. All right, so what about division in MIPS? There is an instruction called div, and it's unsigned sister div u if you're not interested in their sign, and if you don't want to know about the overflow, right, or are not concerned about the overflow. So we divide RS by RT, and the result goes into the same high-low registers that we saw in multiplication. So the remainder goes into the high register, the quotient goes into the low register, and again, you need to use MF, move from low, to access the result, to move the result from those high-low registers to general purpose registers like all your favorite S's, T's, A's, V's, and so forth. Okay, so there is no overflow control. There is no divide by zero control. So it's on you. High is mod. Yes, high is the remainder. Mod is a slang for the mathematical notion of the remainder. Okay, so, and yes, it is in high. All right, so now let's talk about floating point, right? That is very exciting. And floating point is the way to represent non-integral numbers. And we can do a very quick example here that I actually have in my notes. Okay, and we start first with the idea that we talked about the 2's complementation for integer numbers. So can you see my Sublime? Okay, cool. So this is just an integer, and why? Well, because the way we assign weights to bits. So what I highlighted are weights. We can only have integer values, right? No matter how we, what ones and zeros we have here, the sum that we will have, from, by getting some of those weights in our sum or not in our sum, the result is going to be only integer because this least significant bit has a weight of 1, 2 to the 0. So there is no way we can have fractional numbers, but we can do some funny things with with range and precision. So here, this example shows that we have a range of 0 to 31 and precision 1. This is unsigned. Okay, what does it mean, precision 1? It means that two values next to two bit combinations next to each other would be different exactly by 1. Okay, so we have like 1, 2, 3, and so forth. And if we want to include negative numbers, we know 2's complementation. So the range changes, right? Because now we have a way to represent negative numbers. So the range is negative 16 to 15, but the precision is still 1. And then we can have, weights assigned so that the weight of the least significant bit is 2 to the 1, which is 2. Can we do that? Yeah, sure. If we are designing our own representation, we can totally do that. So if we did that with our 5 bits and we assigned weights like that, then the range is going to be larger, or twice as large as in the previous example, but the precision is 2. Why? Well, because we would not be able to represent number 1 or 3, right? We can represent 0, we can represent 2, 4, 6, and so forth. Okay, but so precision is worse, but the range is much, correspondingly larger, and we might be okay with that. So there might be applications where we say, well, 1 or 2 close enough, if it's 1, we just say it's 2. Okay, the error in this representation would not be more than 1. Okay, if we have value 1, we represent it as 2, then the value, the difference between the true representation, the true value, and the value in our representation would be at most 1. Right, and in many applications that might be tolerable. And similarly, we can go actually in the opposite direction. We can assign weights so that their exponents are negative. And this is what is called a fixed a fixed point notation, right? So we put this point here. It's largely, we don't really have to put it because it's just easier for us humans to see that, oh, there's this dot here. It separates fractional part, this, from the integer part here. Right? But we can totally do that. And if we came up with the format like this, we have a range of -8 to 7.5, but the precision is twice better than in this case. Okay, so you see how we can go with double the precision and double the range, right? So if precision gets twice as bad, range gets twice as good. And obviously in the opposite direction, precision of 0.5 is better, right? We have better precision because the difference between two numbers that we can represent, two adjacent numbers, is now 0.5 instead of 1 or 2 in those cases. Yeah, lower precision number is better. It means more precision, right? So I'm a little sloppy with my notation, but hopefully it makes intuitive sense that precision means the difference between two numbers that correspond to two adjacent bit combinations, right? If we change this 1 to 0, right, their number is going to change by 0.5. The value is going to change by 0.5. All right, so and that's the idea behind fixed precision. We can just use weights with negative exponents. Note that it's different from a negative weight. So for the 2's complement notation, we need a negative weight here. Okay, that's our way of getting negative numbers. Negative exponent in the weight it just means we can have fractional, instead of having weights 1, 2, 4, we can have weights 1/2, 1/4, 1/8, and so forth, depending on this exponent. And that can be very useful. And here are a few examples that please review them for for fixed precision numbers, right? If you understand fixed precision, you will have a much easier time understanding floating point numbers. All right, so this is an example that shows, all right, so the delta is in many programming languages, you can actually see, you can have this ULP function, right, that gives you the difference between two adjacent values. That's what we previously called precision, right? So it's 0.1 to 5 in this example. And of course, you can do math here, and this is something that we already discussed, like 1/3 we cannot represent exactly in decimal. It's always a representation. And for the same reason, in binary, we cannot represent 1/10 exactly, or 0.1 exactly. We can get very close to 0.1, but we'll never get it exactly using a finite number of bits. It's always going to be an approximation, right? So if we, in this example, right, that's the closest that we can get. All right, so that's the idea behind the fixed point. So the floating point is similar to scientific notation we use in decimal, right? Instead of having to write something like 2, 3, 4, and then a whole bunch of zeros, we want a shorter notation called a scientific notation. And usually with a scientific notation comes something that is called normalization. So we say, well, this is a scientific notation, but it's not normalized because we still have a bunch of zeros here that we can kind of move into their exponent, right, and have all our values represented in a uniform or normalized way so that it is exactly between 1 and 10, right? So here the rule for normalization is that it has to be greater than 1 and or equal to 1, and less than 10. Okay, so 9.99 is fine, but that's it. Okay, and so we can always do that because we can move this point. Every time we move the point by one position, we have to divide or multiply by 10. That means that our exponent increases or decreases by 1. So we can always normalize the value. In binary, it's the same idea. We want in the normalized representation to have all values represented like that. So first, it's 1 point something, and 1 point something means that, well, if those x's are all zeros, it's 1. So our normalized value is 1 or greater. And in the worst case, we have all those ones, okay, here. So that means that the value is just slightly less than 2. All right. So it is not a coincidence. In the decimal system, we had less than 10 because it was a decimal system. In the binary system, we have less than 2 because it's a binary system. Okay. So that, and then everything else should be captured with their exponent. And of course, exponent is base 2 in the binary system. All right, so that's the idea, and this idea was captured in a 1985 standard that is known as IEEE 754. Right, so colloquially we just say IEEE 754. You don't have to, always say this 1985. 1985 is really the year when it was adopted. And before that, it was, before the standard was passed, it was a wild west. So every vendor, every processor manufacturer, they tend to have their own formats for representing floating-point numbers. Those standards were different. Well, they were not even standards. They were just different ways of doing things. They were all different, and it was very hard to write software that would be compatible with different hardware, and clearly a common approach was needed. And now you probably won't find anything but IEEE 754. So it is a universally adopted standard. According to the standard, there are two ways, two formats. Well, there's actually more than two. So there's single precision and double precision. They are the most common, but there's also quadruple precision, 128 bits, which is not used that much, and single and double precision are most common. Okay, so in many programming languages, single would correspond to data type float, double would correspond to data type double. Okay, obviously they differ in precision as follows from the name, but they also differ in the range of values. And here is the format. Note that it's not a just complementation; it's resembling their SME representation that we talked about, sign magnitude notation. So 1 bit is used to represent the sign, and the encoding is pretty straightforward. 0 means non-negative, 1 means it's a negative number. And then this field for sign is followed by 2 more fields, exponent and fraction. Right? So the exponent is this part, and we'll talk about the bias in a minute. And the fraction is this part. Why is it 1 plus fraction? Well, because we know that it has to be this in a normalized form. So this is what gets stored. And this 1 dot, we don't really need to store it because we always know that all normalized numbers will have this 1 dot, 1 point something. And that's why this is called a hidden bit, right? It's not actually stored, it is assumed. But when we convert a number, of course, we have to remember, that, oh, this one is here, right? So we need to make sure that we remember about it. So the fraction, when we add 1 to it, right? So the fraction is, less than 1 by itself, right? Because it's just this part to the right of the dot. And when we add 1 to this fraction, right? Because we know it's a normalized number, we get what is known as a significant. So fraction plus 1 is known as significant. And the significant is between 1 and 2. It can be 1.0, but it is strictly less than 2. This is exactly in line with what we wrote here when we were doing our preliminary analysis of this format. And so, well, of course, significant by absolute value. All right, so yeah, significant is fraction with this hidden bit 1 restored. So it's 1 point fraction is what is known as a significant. Exponent, right? Obviously, exponents can be positive and can be negative, right? As in the decimal, right? This is a positive exponent. This is a negative exponent. And, we could have used their 2's complementation to store this exponent. But since the range of their exponents is fixed and fairly small, they came up with a better idea. To make our life easier, let's store this exponent as a number which is always positive. So how do we do that? Well, what if you need to store a negative 127, but you want this, and you know that this is the minimum value that you need to represent, and you want to store this as a positive, as a non-negative value. You just say, well, we're going to add a fixed bias. So you say, I'm going to add 127, and then this becomes 0, which is non-negative. If I had a negative 126, that would be 1, okay, and so forth. So this is the real value that you want to, your exponent to be, but this is what you store as the exponent. And what you store is always non-negative, which makes it easier to perform arithmetic operations, so you don't have to mess around with 2's complementation. That's the idea behind the bias. So whatever the exponent here is in the representation, if you want to convert it to, if you want to find out which number in decimal notation stands for it, you have to take this exponent and subtract bias, because when we were storing our exponents, we were adding bias. So 127 is bias in this case. So if you perform an opposite operation, right, if you're going from the representation to the value of the number, you have to subtract bias. And bias is fixed for a given IEEE 754 format. So for single precision, it's 127. For double precision, it is 1203. And based on this, you can find the range for single precision values. So just given those exponents, you need to remember that these exponents are reserved, so they have a special meaning. All other exponents, you just take the exponent value, subtract your bias, and this is their actual exponent. And that's how you convert values from their IEEE 754 representation to decimal notation. And similarly for the largest value. Okay, and for double precision, it's exactly the same, just the lengths of fields are different, and their bias is 1023 instead of 127. Everything else is the same. So the precision that IEEE 754 gives you for single precision is about 6-7 decimal digits. For double, it's about 15-16 decimal digits. It's not uniform. That's why you see it's roughly equivalent, and we say 6-7 or 15-16 for the case of double. So it's not fixed, but it is roughly in that range. All right. So we did the binary refresher already. Okay, and so we can skip that. And exponent identities, you hopefully remember from middle school or high school or whatever. So we've used them already a lot. Okay, and so here are 2 examples that show how to perform conversions. I have more examples of conversions in this file convert.txt. Please review those examples. And you also have the homework on this. Okay, so if you just know the standard, then this is pretty much hopefully intuitive, hopefully straightforward. One other thing that you need to know, particularly for the homework, that we have special values of the exponents that we just mentioned. They have a special meaning. So if their exponent is all ones, it is infinity, and the sign says whether it's positive infinity or negative infinity. If their fraction is 0. If the exponent is all ones, but the fraction is non-zero, it's a special value called nan, not a number, which you get, for example, if you take a square root of a negative number, or if you divide by, if you divide 0 by 0, something like that. And and finally, the exponent of all zeros corresponds to their so-called non-normalized numbers or denormal numbers. They differ in that they are not normalized, which means for them there's no hidden bit. So hidden bit is 0. And when you convert them, you just take 0 instead of 1 point something for normalized numbers. That's the difference. And you know if it's a normalized number or not by looking at their exponent. Okay. All right. Yeah. I'll open this quiz. I will keep it open for like at least an hour, so that you have a chance to finish it, and then we will continue with floating point addition next time. It's 1:51. Sorry for taking one additional minute of your time. Hopefully you enjoy this lecture, and enjoy the rest of your day. And I will talk to you again on Friday. Have a good one. Yeah, I will open the poll. Thank you.